Hello everyone, welcome to new class. Today's class is continuation of transformers. Today we will discuss about EMF equation of transformer, the losses in a transformer and different types of transformers. Consider an alternating voltage V1 at frequency F is applied to the primary winding. An alternating flux phi is set up in the core and is given by phi is equal to phi m sin omega t, where phi m is the peak value of flux and omega is the angular velocity, that is omega is equal to 2 pi f. Then the induced EMF in the primary E1 is equal to minus N1 d phi by dt, that is put phi is equal to phi m sin omega t minus n1 d by dt of phi m sin omega t. Phi m is constant and derivative of sin omega t is minus omega into cos omega t, that is equal to omega is minus 2 pi f into n1 phi m cos omega t. Or we can write 2 pi f n1 phi m sin omega t minus 90 degree, that is minus cos omega t is equal to sin omega t minus 90 degree. Therefore, the maximum value of the induced EMF in the primary is, from this equation we get E1m, that is maximum value of the induced EMF in the primary E1m equal to 2 pi f n1 phi m. This is the maximum value and the RMS value is maximum value divided by root 2. That is RMS value of the primary EMF is E1 equal to E1m divided by root 2, that is 2 pi f n1 phi m divided by root 2. From this we get E1 equal to 4.44 f n1 phi m volts. Similarly, we can write E2, that is the RMS value of the secondary EMF. E2 is equal to 4.44 f n2 phi m volts. This is the EMF equation of transformer. Next, we can study the voltage transformation ratio. Let N1 is the number of turns in primary winding, N2 number of turns in secondary winding, E1 RMS value of primary induced EMF and E2 is equal to RMS value of secondary induced EMF. And we have E1 is equal to 4.44 f phi m N1 and E2 is equal to 4.44 f phi m N2. Now the voltage transformation ratio K, denoted by the letter K, is equal to E2 by E1 is equal to N2 by N1. If N2 is greater than N1, then E2 is greater than E1 and the transformer is called step-up transformer. Also, if N2 is less than N1, then E2 will be less than E1 and the transformer is called step-down transformer. Ideal transformer. An ideal transformer has the properties, that is no winding resistance, no leakage flux and no iron losses in the core. Next is current ratio. For an ideal transformer, input VA equal to output VA. That is, we can write V1 I1 equal to V2 I2. Or we can write I2 by I1 equal to V1 by V2. And V1 by V2 is equal to 1 by K, where K is the voltage transformation ratio. So I2 by I1 is called the current ratio and is the inverse of voltage transformation ratio K. Next is the losses in a transformer. The losses in a transformer are of two types, core losses or iron losses and copper losses. Let us study about core loss or iron loss denoted by the letter Pi. Core loss is caused by the alternating flux in the core and consists of eddy current loss and hysteresis loss. Iron losses are dependent on the load on the transformer and remain practically constant from no load to full load. Iron losses are of two types, eddy current loss and hysteresis loss. Eddy current loss. The alternating flux in the transformer core produces an EMF in the core body because iron is a good conductor. This induced EMF in the core will set up currents known as eddy currents. Eddy currents result in loss of power with the consequent heating of the core. The eddy current loss in watts is given by Q Bm square F square T square V, where Q is a constant, Bm is the maximum flux density, F is the frequency, T is the thickness of lamination, and V is the volume of core material. Next is hysteresis loss. Hysteresis loss is due to the reversal of magnetization in the core and is given by P Bm raised to 1.6 Fv, where P is the hysteresis coefficient, Bm is maximum flux density, F is the frequency, and V is the volume of core material. Eddy current loss may be minimized by using thin laminations, and hysteresis loss may be minimized by using a core of high grade silicon steel. Next is copper loss. Copper loss is due to the ohmic resistance of transformer windings, that is both the primary and secondary windings. Total copper loss is given by I1 square R1 plus I2 square R2, where I1 is the primary current, R1 is the resistance of primary winding, I2 is the secondary current, and R2 is the resistance of secondary winding. Copper losses vary as the square of load, hence copper losses are called variable losses. So the total losses in a transformer is equal to constant losses plus variable losses, where constant loss is the iron loss and variable loss is the copper loss. Efficiency of a transformer. The efficiency of a transformer is defined as the ratio of output power to the input power. That is, efficiency is equal to output power divided by input power, but the input power is equal to the sum of output power and losses. That is, efficiency is equal to output power divided by output power plus losses. And the transformer efficiency is maximum when iron loss is equal to the copper loss. All day efficiency. The performance of a transformer is judged by its efficiency as given by the ratio of output power to the input power. But this efficiency is not true for distribution transformers used for supplying electric energy for domestic and industrial use. The primary of the distribution transformer is permanently connected to the power line and hence it remains energized all the 24 hours of a day. The secondary supply little or no load during the major portion of the day. Hence, the core loss occurs throughout the day while copper loss occurs when the transformer is loaded. The performance of such a transformer is judged by all-day efficiency. The ratio of energy output in kWh to the energy input in kWh over the 24 hours is known as all-day efficiency. That is, all-day efficiency is equal to kWh output in 24 hours divided by kWh input in 24 hours. Cooling of transformers. Heat is produced in a transformer by the iron losses in the core and I square R losses, that is copper losses in the windings. To prevent undue temperature rise, this heat is removed by cooling. In small transformers, that is below 50 kVA, natural air cooling is employed. That is, heat is produced, is carried away by the surrounding air. In medium-sized power or distribution transformers are generally cooled by housing them in tanks filled with oil. The oil carries the heat from the windings to the surface of the tank. The oil also provides better insulation for the windings. For large transformers, external radiators are added to increase the cooling surface of the oil-filled tank. The oil circulates around the transformer and moves through the radiators where the heat is released to the surrounding air. Sometimes cooling fans are provided to blow air over the radiators to accelerate the cooling process. Why transformer rating in kVA? We have seen that the copper loss depends on the current and iron loss depends on voltage. Hence, the total loss in the transformer depends upon the volt ampere, that is VA, and not on the phase angle between the voltage and current, that is power factor. The rating of transformer in kW can be written as kVA rating into load power factor. The load power factor depends upon the nature of load, that is resistive, inductive or capacitive. Thus, the kW rating of a transformer will be different at different load power factors. So, the rating of transformer is given in kVA and not in kW. Let us study about the different types of transformers. Power transformer. They are used in generating stations or substations for transforming the voltage at each end of a power transmission line. They are put into operation during load hours and thrown off during light load hours. And this is possible because they are usually arranged in banks and can be thrown parallel with other units or disconnected at will. Therefore, these transformers are designed to have maximum efficiency at or near full load. And normally, the power transformers are rated in MVA. Distribution transformers. The transformers that are used for stepping down the voltage to a standard service voltage and kept near or at the consumer's premises is called a distribution transformer. They are continuously in circuit whether they are carrying any load or not. The core losses would occur for all the time, whereas the copper losses only when they are loaded. Therefore, the designer has to give attention to reduce the core losses compared to copper losses. They must be designed for good all-day efficiency and not for efficiency at full load. Next is instrument transformers. Instrument transformers are used to extend the range of instruments for measuring purposes. And they are of two types, current transformer CT and potential transformer PT. Current transformer. The transformer used for measurement of large current is called current transformer. And the current transformers are used for reducing AC current from higher value to lower value for measurement or protection or control. The figure shows current being measured by a CT. The primary winding is so connected that the current being measured passed through it, and the secondary is connected to an ammeter. The CT step down the current to the level of ammeter. Potential transformer. The transformer used for measurements of voltage is called potential transformer PT or voltage transformer. The figure shows the voltage measurements with the potential transformer. The primary is connected to the voltage being measured and the secondary is connected to the voltmeter. The PT steps down the voltage to the level of voltmeter. Thank you for watching the class. If you like the classes, please like, share with your friends and subscribe my channel.